Hi, today I would like to share with you about the hyper-heuristic approach. So this is the outline of today's talk. So let's see about the search and optimization in practice. Okay, some research start with a real-world problem. So they try to formulate and model the problem. So in order to do this, they have to decide the problem representation, the constraint in that problem, the fitness function, identify all the constraints and what is the evaluation function and so forth. So after they have identified this, then they have to select the algorithm or the method that is needed or that is suitable to solve that problem. So this is algorithm selection or design. So there are two types of algorithm. Either we use exact method or meta-heuristic method. So exact method sometimes we call mathematical approach. And meta-heuristic method, sometimes people say approximation approach, but this term is still debated. When we apply the method to solve the problem, we will get a solution. If we use exact method, we will have optimal solution. But if you use meta-heuristic, we will get a near optimal solution or good enough solution, because meta-heuristic has no guarantee to find optimal solution. So exact method usually suitable for small problem. So research can be classified into two general categories. The researcher attempt to perform algorithm development with aim of designing robust algorithm, that is, algorithm that can perform well over different problems. So this is called type 1. So we start with the algorithm and then we solve the algorithm on different problems. But not many researchers focus on this type. The second type is the application becomes the starting point for the algorithm design, and after analyzing the problem, an algorithm is customized to given problem by incorporating domain-specific knowledge. So we start with the problem, then we identify a suitable algorithm to solve this problem. So many researchers focus on this type. So let me assume our research is under type 2 and we select TSP as our problem. So we start with a problem, then we identify the algorithm. So let's say the problem is TSP and we choose one of the meta-heuristic approach. This is the example of the meta-heuristic algorithm classification. So this is the family of meta-heuristic. And inside meta-heuristic, some people classify as population-based approaches and non-population-based approaches, or they call it trajectory approaches. Some classifications are based on nature-inspired approaches and non-nature-inspired approaches. Some people classify the meta-heuristic in a group of memory-less approaches and the memory approaches. So some people are classified as local search and non-local search approach. Or some, there are many classifications, and it depends on the researcher how they want to group their work or how they want to identify where or which group their algorithm are belong to. So let's say you use a genetic algorithm. So what can you call? Is it a local search? Is it a population-based approach? It is a nature-inspired approaches? Or is it a memory algorithm or memory-less algorithm? So as we know, that genetic algorithm is inspired by the biological method or biological environment, or from the nature how the algorithm is developed. Okay, let's see the example of genetic algorithm. How to classify genetic algorithm? Is it a local search? Some textbook classified genetic algorithm as a local search. But is it a local search? As we know, the local search is a searching method that search the new solution based on the neighborhood. That means the surrounding area. The neighbor of the solution is those solutions that are close to the current solution. But genetic algorithm, when we what we call create a new solution, the new solution is beyond the local area. They can be in other neighborhood. There is no neighborhood structure in genetic algorithm because we use crossover, we use mutation in genetic algorithm. So to me, I do not classify genetic algorithm as a local search, even though some textbooks classify it as a local search. Okay, is it nature inspired? Is it nature inspired? Yes, genetic algorithm is nature inspired. So it designed based on the analogy of genetic. So we have two parents, we do the crossover, we do the mutation, mutate the current solution to get new solution, mix. It's like the biology. So we have two male and female, we mix them to get a new or to get a child. So this is nature inspired algorithm. As you can see here, genetic algorithm is classified as nature inspired algorithm. For this text from Darrow 2002, the textbook, he do not classify genetic algorithm as local search, but other textbook they classify it as a local search. So is it memory? Does genetic algorithm can memorize the previous search? You can see here, this is a memoryless. Genetic algorithm has memory because the genetic algorithm has a pool of solution. It has a pool of previous solution, and the new solution is generated from the current situation. So, in other words, we can say that genetic algorithm has a memory. Then in the group of nature inspired, we have genetic programming, we have the differential evaluation, we have scatter search, we have evolutionary strategy, we have particle swarm optimization and colony optimization, simulated annealing. All these algorithms are created based on the nature. So that means the strategy in this algorithm are based on the nature. So how about Tabu search? Is it nature inspired? So you can see that this is a gray area. So some people say it's not nature inspired, some people say it's nature inspired. So it's in a gray area. But to me, Tabu search is not a nature inspired algorithm. Tabu search is actually the local search, but this classification it considered as trajectory search. So it is a trajectory search, but it is also a local search because Tabu search has neighborhood operator where we explore the local neighborhood area. So it should be in local search. To me, it should be in local search, but this textbook do not consider as a local search. So what is actually a local search? It's an iterated local search, stochastic local search, guided local search. This is from this textbook. But actually, simulated annealing is also a local search because simulated annealing also has neighborhood structure where when we explore the neighborhood structure, we will create a neighbor solution. A neighbor solution is a solution in the local area. So that's why we call local search. So these are examples of meta-heuristic algorithm. We have single solution based meta-heuristic, which is a Tabu search, hill climbing, simulated annealing, great deluge, and many more. And we also have population-based meta-heuristic, for example, genetic algorithm, N colony, immune system, B algorithm, harmony search, scatter search. There are many more population-based approaches. So this is just example. So this is the revision about the hill climbing. So in hill climbing, we create an initial solution, or we start with a new solution. We start with any given initial solution. Doesn't matter how you create an initial solution. Either you create it randomly or you create with certain algorithm. That is not the issue in hill climbing. So given any initial solution, hill climbing algorithm will start to generate a new solution by using a neighborhood operator. So we have to define what is the neighborhood operator that are going to be used in the hill climbing. So when we apply the neighborhood operator, we will get a new solution. So calculate the quality or the fitness of new solution. If the generated solution or if the neighbor solution is better than the current solution, then we replace the old solution with the new neighborhood solution, new neighbor solution. So we update S equals to S1. Otherwise, discard the new solution. Discard the new solution. So then we test. Do we reach the stopping condition? The stopping condition can be the number of iteration. We set the maximum number of iteration, or we set the time elapsed, the time end. So it depends on the researcher. What is the what we call what is the termination condition? Or you can say that after non-improvement for certain iteration, then we stop. So you need to decide when to stop. If the stopping condition is not satisfied, then we repeat for the to generate a new neighbor solution. The simulated annealing also start with a given initial solution. How we will create the initial solution is not the issue in the simulated annealing. So simulated annealing start with a given initial solution. So don't say that you make an improvement of simulated annealing by introducing a method to generate an initial solution, because simulated annealing will just start with a given initial solution. So then generate a neighbor solution from the initial solution, then calculate the quality of fitness or the quality, calculate the quality of the solution or the fitness of the solution. Then we test. If the new solution is better than the current solution, then we replace it. So else, we test on the acceptance criteria or acceptance rule of simulated annealing. If it is accepted or if it passed the acceptance criteria, then we update the solution with a new solution. Otherwise, we discard the solution. So this is where the simulated annealing and hill climbing are different. Only the acceptance criteria. So hill climbing only accept good quality solution, but simulated annealing can accept a little bit worse solution in order to escape from being trapped in local optima. So simulated annealing can accept a little bit worse solution, depend on the simulated annealing acceptance criteria. So again, we test either we reach or we satisfy the stopping condition. Same like hill climbing, the stopping condition is depend on the researcher. Either you want to stop after certain number of items of non-improvement, or you stop with the time, or you can say in simulated annealing we have the temperature. If the temperature reach nearly zero, then we stop for no more improvement. So you can have few stopping condition if you wish. So sometimes we don't have to wait until zero to stop, because it might take very long time. because after at the end of the search, the temperature is almost zero, and similarity annealing will behave like a hill climbing algorithm, because at the end of the search, it is very hard to accept worst solution. Then we stop and return the best found solution. Okay, let's revise on the Tabu search. Same like hill climbing and similarity annealing, the Tabu search start by given an initial solution, we generate a set of neighbor solution of S that are not in the Tabu list. So this is where Tabu search is different from similarity annealing and hill climbing. Because in Tabu search, we will generate a set of neighbor solution. It's not just one neighbor. We will generate some neighbors of S solution that are not in the Tabu list. So there's some neighbor which are restricted. So this is what we call Tabu list. So calculate the quality of fitness of all the solution. Select the best solution among them and replace the current solution. So this is also different with similarity annealing, and so we will just choose the best neighbor and update the current solution. So the best neighbor might not be better than the current solution. And then we update the Tabu list. So Tabu list is also one of the elements that differentiate between Tabu list, similarity annealing, and hill climbing. So in Tabu search, we have Tabu list. So Tabu list is used in order to avoid revisiting the state that is already visited previously. So the new neighbor is generated, or the new neighbor is considered only if they are not restricted by the Tabu list. Then again, we check the stopping condition. Okay, let's have a look on this example. Let's say we create an initial solution S. If our problem domain is a traveling salesman problem, how to generate the initial solution? This is one question. So we can generate the initial solution randomly. We can generate using nearest neighborhood or farthest neighborhood. So this is called constructive heuristic. So we have to decide how to generate initial solution. So which one is the best? Or which one is good? Okay, how to create an initial solution S? We may create using a random algorithm, nearest neighborhood, farthest neighborhood. So there are few algorithms to create an initial solution for traveling salesman problem. So what is the best way to generate the initial solution? And which method is the best? I mean, which method can produce best solution? The most straightforward answer to the above question might be to employ trial and error to find the appropriate method or operator. Whilst these answers seem reasonable, in terms of computational time involved, it is impractical in many real-world applications. Furthermore, different search methodologies coupled with different operators and parameter setting may be needed to cope with the problem instances of or different problem domains. How to generate a neighbor solution? Okay, let's say we have get an initial solution. Let's say we already created an initial solution. Now, the next question is how to generate a neighbor solution. So we can do, let's say, move one city, swap two cities, or move two cities, and many more. The question is, what is the best way to generate a neighbor solution, and which operator is the best? Within this context, automated heuristic design has emerged as a new research trend. So there are search methodology that is able to provide solution to a wide variety of problem domains rather than being tailored for each problem encountered. So hyper-heuristic represent one of these approaches. Hyper-heuristic operate on the search space of heuristic called low-level heuristic rather than operating directly on the solution space, which is usually the case with meta-heuristic algorithms. So what is hyper-heuristic? It is defined by Burke et al. In 2010. A hyper-heuristic is an automated methodology for selecting or generating heuristic to solve hard computational search problems. So this is the idea of hyper-heuristic. On the left side is the standard heuristic search. So the heuristic operates directly to the solution space. But in hyper-heuristic, we have two layers. One is hyper-heuristic layers, we call higher level heuristic that manage the heuristic, and the heuristic level will manage the solution space. You may think of hyper-heuristic as a supervisor that manages the choice of simple heuristic or operators such as low-level heuristic at any time. So a generic hyper-heuristic framework has two levels known as high-level heuristic and low-level heuristics. So the high-level heuristic will manage or operate on the low-level heuristic. So the high-level heuristic is problem independent. During the problem-solving process, the high-level heuristic decides which heuristic should be called at each decision point in the search process. So the low-level heuristic corresponds to a pool of candidates of heuristic or component of existing heuristic which operate directly on the solution space for a given problem instance. So the high-level heuristic can be a random hyper-heuristic, reinforcement learning, or any type of meta-heuristic. We can have, like, say, symbiotic annealing hyper-heuristic. We can have genetic algorithm, scatter search hyper-heuristic, memetic algorithm hyper-heuristic, harmony search hyper-heuristic, and many more. We can take the idea of any meta-heuristic approach and apply as a hyper-heuristic. So the low-level heuristic can be a constructive heuristic or improvement heuristic. So this is the hyper-heuristic generic framework. So we have hyper-heuristic, in the hyper-heuristic, we have high-level heuristic. Inside the high-level heuristic, we have selection mechanism. Because at this level, the heuristic need to choose which heuristic to be applied. So we must have selection mechanism. So how to select? So we can use any method to select the low-level heuristic. So many researchers design how to select the low-level heuristic. And some researchers focus on the acceptance criteria. How to accept the solution written by the low-level heuristic. And then we have the domain-independent information acquisition and processing. So in between the high-level heuristic and low-level heuristic, we have a domain barrier. So this domain barrier is a domain-independent information acquisition and processing. So at this barrier, the high-level heuristic only need to know the information about the change of candidate solution, the change of candidate solution quality, number of low-level heuristic, measuring the performance of applied heuristic, the statistical information, and many more. So this is domain-independent information. So at the low-level heuristic, we have a heuristic repository. We have low-level heuristic 1, low-level heuristic 2, and many more. So this low-level heuristic can be just a move operator, swap operator, or can be like a pool of meta-heuristic. So it can be as simple as just a 2-op or just a move operator, or it can be more complicated, like maybe you can have genetic algorithm inside the pool. Maybe you can have harmony search inside this low-level heuristic pool. So the selection mechanism at the high-level heuristic will select which heuristic, which low-level heuristic to be applied. By using the selection mechanism, the high-level heuristic will select one of the low-level heuristic. So once it is selected, it will be applied to the solution. So we will apply this heuristic and we will generate the solution using the selected low-level heuristic. So at this level, we need problem representation, we need problem instances, evaluation function, and it might be a single solution, or perhaps it can be a population of solution. So once the low-level heuristic generate a new solution, it will pass to the high-level heuristic to decide whether to accept the generated solution or not. So at low-level heuristic, we can have a population of solution generated by the low-level heuristic. But the low-level heuristic will pass, might be just one solution to the high-level heuristic. So when the solution is when the solution generated by then is submit to the high-level heuristic, the acceptance criteria at the high-level heuristic will decide whether to accept or reject the solution. And then the high-level heuristic will evaluate the performance of the low-level heuristic in order to decide for next iteration, are we going to apply the same low-level heuristic, or we should select another low-level heuristic. So this decision is determined by the high-level heuristic. Okay, let's see how the high-level heuristic select the low-level heuristic at each iteration. So why many researchers choose hyper-heuristic? One of the reasons is generality. Hyper-heuristic can simply apply to another domain with just a little effort. So we have hyper-heuristic. It will operate on the heuristic space, and the heuristic will operate on the problem domain. Let's say the problem domain is timetabling problem. So then we can just use the same algorithm and apply to the domain 2 and domain 3. So then we can test with a minor modification, just apply the high-level heuristic to different problem domain. Of course, the problem domain need to be customized because of the solution representation, the evaluation function, and so forth at the domain-specific knowledge. So another reason why we use hyper-heuristic, hyper-heuristic focus on heuristic selection or generation. This is called constructive or improvement heuristic. Hyper-heuristic can generate a novel searching methodology by using existing component, not only focus on the algorithm configuration. So by switching between several heuristics, hyper-heuristic can make a big impact on the solution quality. So when we use a hyper-heuristic, we can combine or we can automatically hybrid many meta-heuristic approach in one framework. So in other words, we might say that hyper-heuristic is a hybrid heuristic. So according to Rice, 1976, when we select or generate new heuristic, we design a new algorithm which is better than just adjusting its parameter. In 2008, proved that there is free lunch in hyper-heuristic. Thus, it would be possible to design a good method that can work well across different domains. Actually, there is no freelance theorem that no one heuristic can work well across various problems. That means certain heuristic only work on good on certain domain, but it might not be good in other domain. So this is a no freelance theorem. But hyper-heuristic is proven that it can work well across different problem domains.